In part 4, we learned the remainder theorem. In this part, we'll use the remainder theorem to prove the factor theorem. We will then use the factor theorem to factorize polynomials. That is, write a polynomial as a product of lower order polynomials. In a later lesson, we will also learn to factorize using a different method. Why do we need to factorize polynomials? One reason is that we can find the zeros of a polynomial, which is an important task in the application of polynomials, using factorization. Recall that the zeros of a polynomial are the values of x for which the polynomial has value 0. If we could write a polynomial, for example, as x minus 2 times x minus 3, then we can see that the polynomial becomes 0 when x equals 2 or when x equals 3. When x equals 2, the first factor becomes 0, and 0 multiplied by anything is 0. Similarly, the case for x equals 3 occurs. Let us briefly review the remainder theorem. Let p of x be any polynomial of degree bigger or equal to 1, and let a be any real number. If p of x is divided by x minus a, then the remainder is p of a. For example, consider the division of p of x, given here the specific example, by x minus 1. What is the value of a here if we want x minus a to be x minus 1? A should be equal to 1. Without performing division, we can find out what the remainder would be by computing p of a, in this case p of 1. We replace x by 1 in the polynomial, and if we compute it, we get the value minus 5. We can also write the polynomial as p of x equals x minus 1 times q of x minus 5 for some polynomial q of x, where q of x is the quotient. Minus 5 is a remainder. We don't know what q of x is, but we don't need to know it to find the remainder. We are now ready to learn the factor theorem. The factor theorem states that if p of x is a polynomial of degree bigger or equal to 1 and a is any real number, then if p of a equals 0, then x minus a is a factor of p of x. Also, if x minus a is a factor of p of x, then p of a equals 0. Before proving any theorem, it is good to try an example so that we understand what a theorem means before we try to prove it. I am taking an example that we have already studied in part 4, the polynomial 4t cubed plus 4t squared minus t minus 1. We saw in part 4 that this could be written as 2t plus 1 times some polynomial q of x. We don't care what that polynomial is, but we see that 2t plus 1 is a factor. Okay. Now, 2t plus 1 is not in the form of x minus a. So, we need to write it in the form of x minus a. We saw this again in part 4. We can write 2t plus 1 as 2 times t plus half, and t plus half can be written as t minus minus half. So, if 2t plus 1 is a factor, then t minus minus half is also a factor, which means if I want something like x minus a, then a is minus half. So, let us compute p of minus half. P of minus half is 0. This proves that 2t plus 1 is a factor of p of t according to our theorem, okay, because p of a is 0. We know that 2t plus 1 is a factor. So, according to this theorem, p of minus half is 0. We just verified it above. Okay. So, basically what this theorem says is that if p of a is 0, then x minus a is a factor. If x minus a is a factor, then p of a is 0. Now that we understand what the theorem says, let us try to prove it. Let us divide p of x by x minus a to get some quotient and some remainder. By the remainder theorem, p of x equals x minus a times q of x plus p of a. If p of a is 0, then the p of a term drops out above, and so we have p of x equals x minus a times q of x. So x minus a is a factor of p of x because p of x can be written as x minus a times another polynomial. Okay. Now let us say instead we just know the fact that x minus a is a factor of p of x. Okay. Then p of x is x minus a times g of x for some polynomial g of x by the definition of what a factor is. Okay. So what is p of a? P of a is, instead of x minus a, I write a minus a times g of x with x equals a. Okay. So it becomes a minus a times g of a, which is 0 times g of a, which is 0. This proves the factor theorem. Let us do a few examples. Is x plus 2 a factor of x cubed plus 3x squared plus 5x plus 6? We need to check if p of a equals 0 for some correct value of a. What is the correct value of a? Remember, we want x plus 2 to be equal to x minus a. So what should a be? A should be minus 2 because x minus minus 2 is x plus 2. Now we want to check if p of minus 2 is 0. What is p of minus 2? You can replace x by minus 2, and if you do the computation, you will get 0. Okay? So p of minus 2 is 0, so x plus 2 is a factor of this polynomial. I'll give you another polynomial. Okay? It's like the other polynomial except it ends in 7 instead of ending in 6. Okay? So is x plus 2 a factor of this polynomial? We'll check if p of a equals 0 for a equals minus 2. Okay? So what is p of minus 2? If you do the calculation, you will get 1. Okay? So x plus 2 is not a factor because your remainder is not 0. Your remainder is 1. Let us do a slightly more complex example. You are given a polynomial 4x cubed plus 3x squared minus 4x plus k. You are not told what the value of k is, but you are told that x minus 1 is a factor. So can you use this fact to find out what the value of k is? Since x minus 1 is a factor, we know that p of a equals 0 for what value of a? With a equals 1. Okay, because x minus 1 is a factor, so x minus a is x minus 1, which means a is 1. Okay. So p of 1 should be 0. Okay. So what is p of 1? Okay, you can replace x by 1 in this polynomial. What do you get? You will get the value 3 plus k. Of course, you don't know what k is, but you know p of 1 is 0. So if p of 1 is 0, then 3 plus k should be equal to 0. So what should k be if 3 plus k is 0? K should be minus 3. Let us recollect what we have learned today. We proved the factor theorem. Okay. What can we do with the factor theorem? We can check if x minus a is a factor by showing that P of A is 0. Okay. So if we know that x minus a is a factor, then we can find some interesting aspects about the polynomial using the fact that P of A is 0. For example, the previous example we had actually found the value of k for the polynomial using the fact that P of A was 0.